And welcome the presenter for the third paper.
So hello everyone, I'm Zhou Ming from Tsinghua University, and since the authors of the paper do not come here today due to the visa issues, so I'm here on behalf of Kunpeng Zhang to share the paper ShapFuzz. Okay. How can I move to the next slide? Okay. So we'll first introduce the motivation. So fuzzing is a way to test software by using lots of random or partly random data. So, and there is workflow. Here is a briefly workflow of the fuzzing process. First, we have a seed selection process. That's you need to choose some seeds from the seed crops for mutation. And then we have byte scattering. You need to select which position in the seed to mutate. And finally, we have the seed mutation. That is, we need to mutate seeds and test to see if they can trigger bugs or uncover new edges. Due to the vast exploration space of fuzzing, byte scaling has a significant impact on the efficiency of fuzzing. And this paper proposed a solution from the perspective of Shapley fuzzing, or Shapley value. And when mutating an input, there are two main decisions to make. The first one is which bytes to change, and the second is what value to use. To modify bytes, existing methods often analyze input to identify the bytes and their relationship to the conditions, like the comparison operand. And there are three approaches. The first approach is use tent analysis to track the bytes that are related to the conditions. And the second approach indirectly determines the relationship between bytes and the conditions. And the third approach is trying to analyze historical data to determine where mutations should happen. And these solutions provide ways to decide how and where to mutate inputs. And mutant bytes that are related to constraints can help find new code more efficiently. However, not all constraint-related bytes can lead to discovery of new code. Unfortunately, current solutions treat all constraint-related bytes the same way, which means time and energy are wasted sometimes on bytes that won't uncover new code. Therefore, we get our insight. That is, we try to quantify the importance of constraint-related bytes, and we prioritizing the mutation of more important bytes to make the fuzzing more efficient. And to achieve this insight, we first need to design experiment to validate our observation. And before I introduce the following sections, it's important to first understand the background of Shapley analysis. And in cooperative game theory, a group of players come together to play a game and achieve a gain. The question arises, how much does each player contribute to the group? Several methods have been proposed to tackle this problem. And the most well-known solution is Shapley value, which is a method for distributing the gain among players in a cooperative game. To be more specific, the Shapley value calculates the weighted average of each player's marginal contribution to all possible combinations of players. Additionally, the Shapley value has been used in various fields, such as measuring the significance of a feature in deep learning models. And as we mentioned earlier, our observation is that not all constraint-related bytes are able to discover new code, and their importance varies. And therefore, we should design we should design experiments and conduct verification. And so we utilize Shapley value to analyze the combination of bytes. To calculate Shapley values of bytes in a seed, we regard the number of the new edges discovered by a combination as a gain. And to obtain a relatively accurate Shapley value for each byte, we run fuzzing with random mutation for 84 hours on a single seed. And we also use AFL++ to conduct fuzzing experiment on 18 programs with a set of initial states. And these 18 programs include various types, such as MP4, JPG, and MP3. Each fuzzing experiment focuses on a single initial state for a program and continuously mutating the selected state without updating the state query. And during the fuzzing process, if a mutation discovers new edges, we recover all subsets of related bugs and test their result. The left figure is a simple example. The right figures illustrates the contribution of the actually the top X% bytes to the discovery of new edges in each program. And the results indicate that only a small subset of the bytes contributes significantly to the discovery of new code. And furthermore, we also analyze the reasons why this happened. We have made the following discoveries. In a program, not all bytes in the input are related to path constraints. Sometimes even among the bytes related to the same path constraint, their contribution to solving the constraint also varies. Additionally, a byte can be also associated with multiple path constraints, which increase its Shapley value. And we also identify indirect coupling and direct coupling in the figure to demonstrate that there are two types of the constraint. And to investigate the occurrence of bytes being related to multiple path constraints at the same time, we examine the compare operator as an example and analyze the overlapping situations of related bytes among the compares among 16 programs. And this experiment indicates that the sharing of related bytes between compares is a common occurrence in the programs. And in conclusion, we have obtained the following insights. Since only a small portion of the bytes contribute significantly to the discovery of new code, Shapley analysis can be used to identify these high-importance bytes, and more energy is assigned to them during the fuzzing. And next, we will introduce the method design of ShapFuzz. And here is the framework of ShapFuzz, which is mainly divided into two parts, and the Shap value computation and the byte scaling based on the Shap value. And next, we'll move to the design of them one by one. And firstly, let's explain how we model the fuzzing process on a single seed using Shapley analysis. And for a seed, the cooperative game is the schedule of bytes on the seed, including the selection of certain bytes and its mutation of the selected bytes. And a player in the game is a byte, and the collision is that certain bytes are mutated together. And since coverage-guided fuzzing aims to discover new code, so we define the gain as the number of new discovered edges by an input. And finally, the characteristic function is that the is a mapping from the from the collaborative mutation and the number of edges found, numbers of new edges found. And with the formulation of a byte mutation, we can calculate the Shapley value for each byte in a seed. And it's also important to reduce the cost of the Shapley value computation. So we found that the multiple seeds are possible to be treated as one from the can be treated as one seed from the perspective of Shapley analysis. For example, if a seed mutates some byte to get seed A, and A would then mutate to get seed B, but they have the semblance, like A and B has a semblance, and therefore we can treat them as a then we can treat it that they are retained from the same original seed, and do not and they can be considered as part of the combination for the original seed. Let's think we can treat the both seeds are in the same game theory play, and then we group such seeds. As a family, so that all seeds in the same seed family participate in the same cooperative game. And to conclude, seeds in family inherit from the same original seed and have the same length. And the family can reduce the overhead of Shapley analysis because it gathers different seeds into the same Shapley analysis. And the left figure represents our tracking of which bytes are mutating, and the right figures illustrate how we dynamically maintain the family during the fuzzing process. And all seeds within the family shares the Shapley value, so we do not need to repeatedly calculate the Shapley value. And so far, we have modeled byte mutation as a calculation process of Shapley value. And thus, during the fuzzing process, we can obtain the Shapley value of each byte in the seed field. And finally, we further utilize the multi-arm bandit model to maximize the efficiency of fuzzing when using the Shapley value. And we will determine which bytes to mutate based on the Shapley value, and the mutator will perform the mutation of the selected bytes. And to make the trade-off between and we also make a trade-off between mutating bytes with a higher Shapley value and bytes with low frequently chosen. And the next step is to introduce the evaluation section. And the ShapFuzzer is implemented based on AFL++, and we have introduced the two main experiments to test its performance. First, we compare ShapFuzz with 5 state-of-the-art byte scattering fuzzers. We analyze the performance on 3 sets of initial seed with different lengths, and we also observe their effectiveness regarding edge coverage and bug detection and analysis time. And basically, we compared ShapFuzz with 5 state-of-the-art fuzzers, including Gray1, ProFuzzer, News, Prefuzz, and Angora. And from this table, with all the initial set provided, ShapFuzz discovered more edges and more bugs than all other compared fuzzers, and ShapFuzz found totally 103 unique bugs, which is 19 more than the best fuzzer compared Angora. And as for the seed smaller than 10,000 bytes, and ShapFuzz found 11 more bugs than the best compared fuzzer. And as for seed smaller than 1,000 bytes, ShapFuzz still discovered more edges and more bugs than all other compared fuzzers. And in this section, we compare ShapFuzz with some commonly used fuzzers to further demonstrate its performance. We select AFL and AFL++, AFL fast, and FairFuzz and MOFT and at the compared fuzzers. And in AFL++, we enable the red king mutator and the MOFT mutator, and we conduct experiment on 2 platforms, UniFuzz and MAGMA. And first, on UniFuzz benchmark, and ShapFuzz discovers the most new edges at both 1 hour and 3 hours. And additionally, ShapFuzz finds a total of 150 bugs, which is like around 20 more than the best fuzzers, which is, I think, AFL++. And Then on the MAGMA dataset, we analyze the first time that each bug is triggered, and ShapFuzz has used the least time to trigger a bug on 29 CVEs, and which has the best performance among all fuzzers. And generally, and overall, ShapFuzz performs best to trigger a total of 46 bugs. I think that's all. And since I'm actually not the author of the paper, so maybe I'm not the proper person to answer the questions. So if you have any question, please just contact the authors using their email.
Okay, so thank the speaker for the presentation. Yeah, so I guess, yeah, no questions, then we should just contact the author by emails if you have any comments.